Okay, when we broke for the last segment, we were looking at composition of compounds. And sometimes it's useful to know sort of what the composition of a compound is in terms of, say, proportions or percentages of elements present. For the purposes of, say, making sure that a person gets a proper dosage of a certain element that's in a medication or something like that, or determining the amount of, say, chlorine that's put into the atmosphere by a certain amount of chlorofluorocarbons, that kind of thing. So we can find the percent by mass of an element in a compound by using the formula and molar masses. There are, of course, other ways that you can find percentage. You could evaluate how much of a given compound is made up of a certain element in terms of, say, number of atoms present, or say the amount of space taken up. But the most common way to do it is by mass. What is the percentage by mass of a given element in a certain sample of a compound? Generally, percentage of anything is equal to the part you're interested in divided by the whole thing times 100. And that has a wide variety of applications. It just depends on what part are you interested in, what is the whole thing made up of, and then you multiply it by 100 to make it a percentage. In particular, in this case, the mass percentage of element X in a compound could be given as say the total mass of X in the sample divided by the total mass of the sample. Okay, and actually you could do this regardless of what amount of the compound you have. If you can find the total mass of that particular element in the compound, then you could find the mass percent of the element in the compound just by taking the total mass of that element in the sample divided by the total mass of the sample. So the total mass of the element X would be the part we're interested in, and the total mass of the sample would be the whole thing. For convenience, we usually set things as basically what's present in 1 mole of the compound. Because that case, if we use 1 mole of the compound, you don't actually need an actual sample of the substance in order to figure out what the percentage of each element present is. All you really need is the formula of the compound and the periodic table. So you wouldn't actually need a real sample of the stuff. C6H12O6. Okay, so if you wanted to find the mass percent of carbon in glucose, which has the formula C6H12O6, then that would be the mass of carbon in 1 mole of glucose divided by the mass of 1 mole of glucose. Times 100. The mass of carbon in 1 mole of glucose would be 6 times the atomic mass of carbon. So for every mole of glucose, you've got, well, basically for every molecule of glucose, you've got 6 carbons. So for each mole of glucose, you've got 6 moles of carbon. So that would be 6 moles of carbon times 12 grams of carbon per mole. And there are 180 grams of glucose per mole. If you add up, 6 times 12 for the carbon, plus 12 times 1 for the hydrogen, plus 6 times 16 for the oxygen, all of that totals up to 180. So 6 times 12 is the part we're interested in, and 180 is the whole thing, if we're talking about 1 mole. So we've got 72 grams of carbon altogether for every 180 grams of glucose. And that comes to 40% exactly. So glucose is 40% carbon by mass. We could also find the percent hydrogen in glucose. So we find the mass of hydrogen in each molecule. There are 12 hydrogens for each molecule of glucose. So that means for a mole of glucose, there would be 12 moles of hydrogen at 1 gram per mole, divided by, again, the molecular mass or molar mass of glucose, which is 12 grams per mole, times 100. And 12 over 180 would be 6.7% hydrogen. And then for oxygen, there'd be 6 moles of oxygen for every mole of glucose at 16 grams per mole. And that's over the mass of 1 mole of glucose. Times 100. And that is 53.3, repeating, percent. And one thing to keep in mind is whenever you find the percentages of everything in a compound, they better add up to 100%. So carbon, hydrogen, and oxygen are the only things present in glucose. So 40 plus 6.7 plus 53.3, it better be 100. And they are. The other thing is that we could have saved ourselves a little effort by noticing that oxygen was the last thing present in glucose. And so since the 3 percentages have to add up to 100, the percentage of oxygen should be 100 minus this, which it is. If you take 100 minus 40 minus 6.7, you get 53.3. We can also use mass percent as a conversion factor between mass of an element and mass of a compound. So for example, for this, if you have 785 grams of glucose, how much oxygen is there in it? Okay, so all you have to know now is the mass of the sample, because we know that 53.3% of any sample of glucose is going to be made up of oxygen by mass. Okay, so when you use a percentage mathematically, you put it back in its decimal form, which means you take the percentage divided by 100. So 53.3% becomes 0.533. And so we have 785 times 0.533. Or you could look at it like this, 785 grams of glucose and 53.3 grams of oxygen for every 100 grams of glucose. That's essentially what percentage means. And in this case, grams of glucose cancel, and you end up with the same 418 grams of oxygen. So whichever way makes more sense to you is the way you can do it, because they both come out the same way, obviously. Another example, if 37.5 grams of oxygen is incorporated into glucose, what mass of glucose results? So say if you're studying photosynthesis, plants take in oxygen and they use it, they incorporate it into glucose, basically, which things like starch, the building materials of plant starch and cellulose are really just made up of glucose molecules chained together in long chains. And so essentially, plants are making glucose from the oxygen they take in from the atmosphere and the carbon and hydrogen that they get from nutrients in the soil, and they make glucose. So you've measured the amount of oxygen available to the plants. You want to calculate the amount of glucose that they should be able to make from that. Okay, well, that uses the same idea as up here, only we're going in the other direction, so we're going to use this upside down. Again, oxygen is 53.3% of by mass of glucose. So if we have 37.5 grams of oxygen, and we know that 53.3% means that there's 100 grams of glucose for every 53.3 grams of oxygen, then we get that there should be 70.4 grams of glucose that the plant can make. And then you could compare that amount to what the plant actually made, and you could sort of judge the plant's efficiency. Okay, so we can get a large number of conversion factors from chemical formulas. And that can be fairly simple, like if you're dealing with numbers of moles, all you really have to do is look at the compound. So the formula of glucose is C6H12O6. It just means that for every molecule of glucose, you have 6 atoms of carbon and 12 atoms of hydrogen and 6 atoms of oxygen. So however many molecules of glucose you have, you're going to have 6 times as many carbons and 12 times as many hydrogens and 6 times as many oxygens. So if you have 7.64 moles of glucose, how many moles of hydrogen do you have? Well, that's just a matter of 7.64 moles of glucose times the fact that there are 12 times as many hydrogens as glucose molecules. So in this case, that means that there'd be 12 moles of hydrogen for every 1 mole of glucose. And that would mean that there would be 91.6 moles of hydrogen. So you might wonder, what mass of hydrogen would that be? Okay, 7.64 moles of glucose times the fact that there are 12 moles of hydrogen for every 1 mole of glucose. And there's 1 gram of hydrogen for every 1 mole of hydrogen. So you notice moles of glucose cancel, moles of hydrogen cancel, and you get grams of hydrogen out. And that would be 91.6 again, because it's 1 gram for every mole. And whenever you want to convert from mass of one thing to mass of another, even if it's, say, from mass of a compound to an element in the compound, you always have to go by way of moles. And we'll do that when we get to more stoichiometry problems. But for now, let's just say what mass of hydrogen is present in 500 grams of glucose. Okay, so we get 500 grams of glucose. We can change to moles of glucose. Okay, so there's 1 mole of glucose for every 180 grams. This would give us the number of moles of glucose. But we don't want that. We want moles of hydrogen. And there are 12 moles of hydrogen for every 1 mole of glucose. But we actually don't even want that. We want mass of hydrogen. There's 1 gram of hydrogen for every mole of hydrogen. And that comes out to 33.3 grams of hydrogen. Or it would be simpler, actually. if you know the percent hydrogen, because if the percent of hydrogen is 6.7%, that just means there's 6.7 grams of hydrogen for every 100 grams of glucose. And you can multiply that ratio by the 500 grams. And guess what you get? 33.3 grams. Same as we got the other way. So this is obviously the easier way if you know the percentages of the elements in the compounds. And in fact, it might even be easier if you have the formula for the compound to just go ahead and find the percentage of hydrogen in glucose and then do the question this way, as opposed to doing it that way. But either way will work. So it's important to remember, though, that what the chemical formula tells you and what it doesn't. Because what a chemical formula tells you is the relationship of the elements to each other in terms of number of atoms or number of groups of atoms. And in chemistry, the most convenient group would be number of moles, not in terms of mass. So that's why we had to go by way of moles. So whenever you want to convert from mass of one thing in a compound to the mass of something else in a compound, you first have to find moles. And then you can convert to mass. So, for example, if you want to convert from the mass of the compound to the mass of an element in the compound, you would have to take the mass of the compound and find the number of moles of the compound. Then you can find the number of moles of the element present in the compound. Then you can find the mass of the element. Essentially, when you want to go from mass of the compound to number of moles of the compound, what you're effectively doing is dividing by the molar mass or the molecular weight of the compound, like we did in the first step in the last example. Okay, once you've got moles of the compound, you can convert to moles of the element by using the the subscripts or the ratios in the chemical formula. And then once you have moles of the element, you can find the mass of the element by multiplying by the atomic mass of the element. Okay, so that's how you have to do it. You can't go directly from mass to mass, not in a chemical formula and not in a chemical equation either. Okay, 310 is about writing and balancing chemical equations. This is a pretty important topic because chemical equations are essentially how we communicate what happens in a chemical reaction. An equation is the chemical reaction, or an equation is a summary of a chemical reaction. A chemical reaction is basically a process in which atoms are separated from each other in reactants. Okay, so this is the atoms in the reactants that are separated from each other, rearranged, and that's essentially what the chemical reaction is about, and bonded back together in different combinations. Okay, so you take the atoms apart, maybe not all of them, but at least some of the atoms, you take them apart, rearrange them, put them back together in a different way. And that's a chemical reaction. And part of a chemical reaction is that the chemical identities of the substances present have to change. And so we're talking like the molecular formulas of the subject, of the substances have to change. It's not just a change in state, like H2O liquid going to H2O gas when you boil water. That's a physical change, not a chemical change. So that's not a chemical reaction. Although it can be written in the form of a chemical reaction, it's actually not a chemical reaction. Chemical reactions are chemical changes, and vice versa. A chemical equation is just a summary of a chemical reaction. And you read the equation left to right. The reactants are on the left and the products are on the right. And the arrow represents the transformation, which is the reaction itself. The reaction can be read as, reactants form the products, or reactants produce the products, or something like that. And an example of a chemical reaction is the combustion of butane. Combustion is just a fancy science word for burning something in the air. Butane has the formula C4H10. It's a gas. If you look at a butane lighter, actually, you may, if you have one of the transparent ones, you may see liquid sloshing around inside. That's actually butane. That's because butane is a gas at normal room pressure and normal room temperature and at normal atmospheric pressure. But if you put it under a little bit of pressure, then you can turn it to a liquid. And inside the lighter, it's actually under a little bit of pressure. That's why the walls of the lighter are fairly thick, so that they can contain that pressure to maintain the butane as a liquid, just because it's more dense when it's a liquid. The lighter will last longer if you condense the butane into a liquid, because you can fit more of it into the lighter that way. But then the moment you press the little lever and it opens the valve, the butane comes out, and as soon as it hits the atmospheric pressure, it will become a gas again. And in fact, if you press the little lever without turning the wheel to make a spark, you can actually put the lighter up to your ear and you can hear a little tss, and that is the butane turning to a gas and coming out into the room. When the butane combines with oxygen in the air, it forms carbon dioxide and water vapor. It's water vapor because this is happening at a high temperature, and also gives off quite a bit of energy. The energy part may or may not be included in the chemical equation. Usually it's not, but there are some cases where you might be interested in that. And so you can include that or not. Now, in this case, we've got the right reactants and the right products, but that reaction that I just drew violates the law of conservation of matter. And that's because if we look at the number of atoms of each element, you'll notice that the number of atoms of each element coming out are not equal to the number of atoms of that element going in. So if we look at carbon, hydrogen, and oxygen in this little equation that we've written here, you'll notice that there are 4 carbon atoms going in. Each molecule of butane consists of 4 carbon atoms and 10 hydrogen atoms. So that's 4 carbon atoms going in. Coming out, we've only got 1. 3 carbon atoms just disappeared into nothing. And that cannot happen. So right away, we know that we've violated the law of conservation of matter. Hydrogen, we've got 10 going in and only 2 coming out. Each H2O molecule has 2 hydrogens in it. So 8 hydrogen atoms have disappeared into nothing. And let's see, for oxygen, we have 2 going in and 3 coming out. So we've created an oxygen atom out of nowhere. And that cannot happen. So we have to balance the equation in order to make it conform to the law of conservation of matter. And the way we do that is by balancing the reaction. That's what it's called. For balancing a reaction, there are a couple important things to remember. In balancing a reaction, you're trying to get the reaction so that it obeys the law of conservation of matter. But once you've decided what the reactants and products are, and you've written down the correct chemical formulas for those reactants and products, you cannot change those formulas. Because if you change the formula, you change the identity of the compound. And that means that if you need more or fewer atoms of a certain element, you cannot get there by changing the subscripts within the formulas. So once we decide what the reactants and products are, and we write down the correct formulas for those reactants and products, you cannot change the subscripts from that point. And that's simply because changing the subscript means you're changing the compound, and the reaction wouldn't be true anymore. But what you can do is you can change the number of molecules of a reactant or a product. And you do that by using coefficients. That is, large numbers before or after, or before the formula for one or another of the compounds present. And that changes the number of molecules. And if you change the number of molecules, then of course you change the number of atoms of the elements within the compound. Okay, so to balance an equation, balancing can often be achieved just by trial and error. For all of the equations we see in this part of the course, trial and error will be, a perfectly good way to do it. There are some compounds or some equations that are harder to balance and require specific procedures, but we won't get to those until later. So, we'll wait until then to introduce that idea. Before we get to the rules for balance, and of course there are some rules, even for trial and error. And the reason is that if you just go into it blindly and start balancing one thing, whatever happens to pop to mind first, then you can get caught in kind of a vicious circle where you change one thing, but that changes something else. Then you have to go back and change the other thing, and then you go around and around and around and never actually get it balanced because you're always changing something. So there are some, a few minor rules to keep in mind when balancing by trial and error. And we will pick those up in the next segment because I see we're over 30 minutes. So see you in a